Hi, welcome back. What comes in and out the balanced mixer on this side is connected to the same biamp that is described in the MU by ITX. It uses more transistors than the original concept, but with this one the impedance of the output is not defined by the input and vice versa. As can be seen, built in Manhattan style, on a small copper board that is soldered afterwards to the large board. Because it is 50 ohm in and out, it could be connected directly to the mixer. The other side is connected via a small transformer to the crystal filter. To give some idea about the levels, from the mixer is coming about 1 milliwatt to this amp with three transistors, and then you have about 73 milliwatts here. But then it goes into the filter, the crystal filter, and what's coming out of the crystal filter is only 1.5 milliwatt. So this filter gives a lot of attenuation, about 17 dB. That's a lot, but we've gained enough, so no real problem here. The crystal filter is designed in accordance with QAX November-December 2009. I will give a description in the link below. It says how you can do it, and in this case they have a schematic of an 8-pole filter, and I made the 12 MHz filter with 6 poles. I made the crystal filter with this kind of crystals, 12 MHz. I numbered them and put them in the Excel sheet to sort out what the best values are. I used for that a tool with some capacitors and an IC socket to sort out what the frequencies are the crystals are performing on. I measured the curve by using the SI5351 output and an HP milliwatt meter. With small steps manually key in changes in an Excel sheet. As you can see, if the value is the same, I didn't write down anything, and changes I wrote down. This is not the most handy way, but it worked, and the data can be seen in a graph with a logarithmic scale. And by changing the numbers of turns of the transformers, I could see that the bandwidth is not really influenced, but the flatness is. As you can see, this color here is without the transformers, so the bandwidth is this size, and it has a lot of dips in the passband. And with the transformers, the transformer 1 I used, you get the same bandwidth, but it is already more flat. Then I changed some capacitors to make the bandwidth some wider, and then you get the ripple again back, but with a new transformer, more windings, it has the flat shape again. The schematic, some obvious things. You would expect the B-amp like here before the filter, also after the filter. However, I had enough RF available after the X-Tel filter to drive the SRA1 double balanced mixer. So I have only for receiving 1 amp, and for transmitting I use a diode switch. During TX I do some voltage here, and the diode will flow the current through, and the signal is also passed in that direction. After the X-Tal filter here we have 70 dB of carrier suppression, and first started also here with an amp, and it resulted in bad carrier suppression because of pickup of the local oscillator signal. That was also the reason why I completely made it in an enclosure. With 5 milliwatt here at 62 megahertz and 1.5 milliwatt 12 megahertz coming from here, this results in a 0.23 milliwatt mixer output, and the frequency here is then of course 62 minus 12 is 50, that is the wanted frequency, and also 62 plus 12 is 47. You can also make 4 meter band transceiver out of it, but if you do here your clock 0 from the SI frequency board completely different, then you can also make it a 2 meter transceiver. Next time, to the filter, the wanted frequency, and see you again.